Welcome to another edition of RCE. I'm your host, Brock Palen, and I have again Jeff Squires from Cisco Systems and the OpenMPI project. Jeff, once again, I hear you have a blog.
Again, just like you were prompted to say that, yes, I do have a blog where I muse on MP and high-performance networking kinds of things, and would encourage everybody to go have a look at it because it makes me look good among my Cisco fellow bloggers.
Yes, and we have a link to that straight off of our front page at rce-cast.com, where we have all of our old shows, an iTunes feed, an RSS feed, as well as you can download the MP3 directly from the site there for any old shows, as well as see who we've had, see who we plan on having, and also submit a nomination for any other topic you'd like to have on the show.
Yeah, we might as well mention the whole social network. Working too, Brock, you have a Twitter account there, and we accept questions for upcoming RCE podcasts from random people. So if there's something that you want to ask somebody on a future interview, please tweet that to Brock.
Yep, my Twitter is Brock Palen, BrockPalen, and that again is on the RCE website. So let's go ahead and get into our topic for today. Today we have two people from University of Tennessee at Knoxville. We have Jack Dungera and Jacob Kurzak, and they're both from the Plasma project, and I'll let them explain what that is specifically, but I believe it's a lot of work for doing parallel linear algebra, but they can go into that specifically.
Sure, Brock. This is Jack Dungera. I'm a professor here at the University of Tennessee at Knoxville, and I'm in the Electrical Engineering and Computer Science Department. I also have a position at Oak Ridge National Laboratory, and occasionally spend some time at the University of Manchester in England. I'm interested in high-performance computing, designing algorithms and software for those systems. I also have an interest in performance analysis and in how affect parallel programs and applications. I've been here at the university for about 20 years now. Before that, I was a researcher at Argonne National Lab outside of Chicago, and I guess before that I was a student at the University of New Mexico in the applied math program there. Jacob?
This is Jacob Kurzak. I've been working with Jack for 4 years now in the linear algebra group. Software like LAPAC, Scalapart, and most recently Plasma and Magma. Before that, I did my PhD at the University of Houston, mostly doing large-scale problems in molecular design.
Okay, so let's move right in. Plasma, what is the motivation behind it, and what is it specifically first?
Right. So Plasma stands for Parallel Linear Algebra Software for Multicore Architectures. And here at the University of Tennessee, along with some colleagues at various places, Jim Dummel at Berkeley and colleagues really around the world, we have been involved in the design and implementation of algorithms and software for linear algebra. And in my case, this goes back to really 1970, late 70s, when we designed a package called LinPack. So LinPack was a package of linear algebra software for solving systems of linear equations. And when it came out, it was sort of revolutionary. It relied on a small package called the Basic Linear Algebra Subprograms, the BLAS. And at that time, there was only one level of the BLAS, namely vector operations. So LinPack was a beginning of I'll call it a standardization process in linear algebra software. It quickly became apparent with the advent of new machines, different kinds of architectures, in particular, not vector machines, but shared memory, parallel systems which had cache as their basic operation mode for exploiting performance, that we had to redesign the algorithms. And that's when we designed, Jim Dummel and I designed a package called LAPAC, Linear Algebra Package, and that was done, it was done in the 80s, in the late 80s, that package was created. And that was in use for many, many years. It contains software for linear systems of equations and eigenvalue problems, and has enjoyed, again, widespread use, became a standard, is adopted by almost all the vendors and commercial software, numerical software companies. But it became apparent with the advent of multi-core architectures that some changes were necessary in the fundamental design of that package, and that brought about Plasma. So Plasma was designed specifically for multi-core, initially for shared memory multi-core architectures, and the design basically took a step back and looked at the overall structure of the algorithms and tried to understand what the issues were in terms of exploiting multi-core and trying to gain high performance in light of that. It's clear that multi-core is more than just 2, 4, or 8 cores. It's going to go on. We would guess somewhere between 100 cores we would see in the near future, and potentially even greater numbers, perhaps up to 1,000 cores per socket in the foreseeable future. And we wanted to design a package that would take us through tens to hundreds to thousands of cores on a socket, and that's what Plasma is attempting to do.
So what's your main mode that's different for extracting performance from many cores on a single linear algebra solve with Plasma versus something like LAPACK, which many people have used?
Right. So LAPACK is based on a very common technique for exploiting parallel processing. It's the fork join model. So you have a sequential thread. It comes to a point where it can fork off a number of things in parallel. Think of loops, a loop being run in parallel, a number of independent processes being spun off, and then waiting for all those processes. So many of our algorithms can be structured in a very, I'll call it, simple way to fit into that this fork join kind of parallel process system. And LAPACK is built around that in terms of splitting off things for operations that deal with the level. So if you're going to be one of the level 3 laws, which is engaged most often, is matrix multiply. So the sequentialized part of the code, and then we encounter a matrix multiply operation where we think about forking off a number of tasks to do that matrix multiply, and then we wait until all those tasks are finished, and then we carry on the computation. So there's a fork join, bulk synchronous kind of operation that goes on, and that was okay for a certain level of parallel processing. But with multi-core, that breaks down. It breaks down very quickly. Of course, it works, but the performance suffers. We see nowhere near the kind of performance that we would hope to see out of the current generation and presumably next generation multi-core architecture. So we want to break the fork join parallelism. And we've been doing that and experimenting and looking at various ways people have expressed parallel processing in the past. And so today we're using a technique which is not a new technique, it's an old technique, but we're expressing the algorithm in terms of a directed acyclic graph. We're looking at small tiles of work, small blocks of computation that can be done, and unrolling basically the algorithm at a very high level to expose a lot of parallelism, to get a DAG which is very wide, which shows its great depth in terms of parallel processing. So at a very high level, our algorithms are expressed in terms of DAGs, and we execute the DAG on a multi-core architecture.
So you break them up into tiles and so on. How exactly do you map that to multi-core architectures? Are you actually doing things like examining cache sizes, examining shared caches, and examining the memory hierarchy as well, or how do you assign that work?
Well, so there is a stage in the I'll call it deployment of the software, which looks at